This is ARIS, the Autonomous Rescue and Inspection System. It is a differential drive rover built to navigate structurally compromised environments. On top, we have the multimodal sensor array, an MQ6 gas sensor, an ETSI SR04 ultrasonic sensor, and MPU 6050 IMU mounted depth center with vibration damping. To prevent motor stall currents from browning out the logic board, I engineered a strict dual power architecture, separating the high current Duracell motor pack from the ESP32's dedicated power bank. When powered on, the system requires a 3-second stationary boot window. During this time, the ESP samples the IMU to calibrate and calculate the Z-axis gyroscope drift offset. Moving the rover now would corrupt its heading baseline. To verify the system's integrity at the deepest level, I utilized the serial monitor to observe the ESP32's bootloader and hardware handshake. Here we can see that the internal code initializing SPI flash and calibrating the internal clocks. This diagnostic output confirms that the hardware is healthy and the memory is ready to execute our custom ARIS firmware. While this low-level data is strictly for debugging, it provides essential verification that our I2C bus and sensor peripherals are physically accessible before autonomous flight state machine takes over. The asynchronous WebSocket setup. To maintain a responsive control loop, I implemented an asynchronous architecture using ESP async web server and async TCP libraries. Unlike standard blocking web servers, this allows ARIS to broadcast telemetry to the command center without passing the main execution thread. By offloading the web traffic to a background process, the rover can process sensor data and adjust motor speed with zero latency. Now coming to P-controller and IMU calibration. Reliable navigation in a disaster zone requires a stable heading. During the boot sequence, the code samples 200 readings from the MPU 6050 to calibrate the Z-axis gyro drift. In the exploring state, I use the proportional feedback controller. It calculates the error between the current yaw and the target bearing, then dynamically adjusts the PWM duty cycle for the left and the right motors to keep the rover on a perfect straight path. The brain of the system is a finite state machine. This logic ensures that the ARIS always prioritizes safety. If the MQ6 sensor analog reading exceeds our threshold on ADC1, the state machine interrupts all other processes to halt the motor and pulse a hazard alert. Similarly, if the ultrasonic sensor returns a distance under 25 centimeters, the system transitions to an invasive maneuver until a clear path is verified. Once calibrated, ARIS hosts its own local network and telemetry dashboard. Standard HTTP web servers block the main loop while waiting for client request, which would cause a moving robot to crash into walls. To solve this, I implemented an asynchronous WebSocket pipeline. This allows the ESP32 to push live sensor data, including distance, air quality, and heading, to the operator 4 times a second, completely independent of the physical motor control loop. In the exploring state, the rover drives forward using a proportional feedback controller to maintain a perfectly straight bearing. When the ultrasonic sensor detects an obstacle within 25 cm, the finite state machine instantly transitions to an invasive maneuver. It executes a closed loop point turn until the path clears, then resumes exploration. To protect human first responders, the rover actively monitors environmental hazards. If the analog reading from the MCQ6 exceeds our calibrated threshold, simulated here with an alcohol swab, this system shifts into a hazard detected state. The motor immediately halts and pulses as a physical alert, and the dashboard updates in real time. Ultimately, ARIS is a direct application of the sense, plan, act paradigm. Raw data from the perception layer feeds into the ESP32, which acts as a processing node, updating the finite state machine and driving the physical actuators. This project bridged the gap between theoretical algorithms and the messy physical hardware, proving that we can build a reliable autonomous system to keep humans out of harm's way.